Let's practice with cylindrical coordinates a bit. We would like to try and express a sphere of radius 3 using cylindrical coordinates. So first let's start with Cartesian coordinates. We know that a sphere with radius 3 centered at the origin is expressed by the following Cartesian equation. And we know the conversion to cylindrical coordinates just amounts to converting the x and y to polar and leaving the z as it is. So here you go. This is a cylindrical equation that represents the sphere of radius 3 centered at the origin. All right, let's go. Did it ask us to do anything else? Let me check. Oh yeah, write an integral for an arbitrary function over the three-dimensional ball. Okay, so now that we have the sphere itself expressed in cylindrical coordinates, let's go ahead and try and express the solid ball with inequalities involving the cylindrical coordinates. So this is a filled-in sphere like that. Well, I can see that in the xy plane, this sphere lives sort of above the circular region, x squared plus y squared equals 9. So in polar coordinates, that would be expressed by letting theta range from 0 to 2 pi and r ranging between 0 and 3. And then what's left is to bound the z on top by the top hemisphere and on bottom by the bottom hemisphere. Well, I can just look at this equation to get that. The top of the sphere is going to be positive square root of 9 minus r squared, and the bottom is going to be negative root 9 minus r squared. So that's the last set of inequalities that we need, and so we can now integrate over the sphere in, oops, I put the negative in the wrong place. There we go. Over this sphere using cylindrical coordinates. So if I have any old integrand function, I just put it in the middle and set up my integrals like this. So theta goes between 0 and 2 pi, r goes between 0 and 3, and then z goes between negative root 9 minus r squared and positive root 9 minus r squared. And then we have our extra r for the polar coordinates, dz, dr, d theta. Okay, and it's a good practice to take all of these quadric surfaces. We just did a sphere, but you can do any one of these guys and write it in a cylindrical equation. Since you have lots of x squareds and y squareds, for example, the hyperboloid of one sheet becomes r squared minus z squared equals 1. And the paraboloid becomes z equals r squared, and so on. So you can fill out the rest of those. If later you're trying to integrate over an object that's formed by a quadric surface, you're going to be doing this. Okay, one last example. Let's use cylindrical coordinates to find the volume of the solid described here. So I've got a sphere of radius 2. There we go. And then a cylinder, circular cylinder that has radius 1. So that would be more like this. So the cylinder is going to cut the sphere, and I want to find the volume of the solid that lies inside both of these things. So that volume is going to be sort of capped on top and bottom by the sphere, and then on the sides by the cylinder. So it's this little like cylindrical cap, or like it's like a pill-shaped region that I'm trying to describe. So I can see that the region in the xy plane that this blue cylindrical portion lives over is just the circle in the xy plane made by the cylinder. So let me start there. That circle has radius 1, I guess. So to express it in polar coordinates, I'm going to let theta range between 0 and 2 pi and r range between 0 and 1. And then what's left to do is express z at most this top hemisphere value and at least the bottom hemisphere value. So it's similar to what we did in the previous slide. This would be negative 4 minus r squared. So I'm just taking this sphere equation and solving for z. That would be the bottom hemisphere, and converting to polar coordinates. And the top would be 4 minus r squared as well. So the volume of this solid, computed by a triple integral, looks like this. So to compute volumes, of course, we're going to integrate 1 in the integrand, but of course I have an r because of the polar coordinates, or cylindrical coordinates, and I do dz, dr, d theta. Okay, and you can go ahead and compute this integral just as an iterated integral. Feel free to go to Wolfram Alpha and see what the result is. I think that's what I'll do now. Okay, it looks like Wolfram Alpha has interpreted the integral that I wanted correctly, and this looks like the answer right here.